In the previous lecture, we discussed the high-level overview of the register allocation algorithm, and the overall algorithm works like this. You first draw an interference graph of the IR registers, and then color the graph. And if the coloring is successful, which means that the coloring number, the number of colors used in coloring the graph is less than or equal to the number of CPU registers, then we are done and use such coloring number to map each IR register into CPU registers. Otherwise, you have to spill an IR register. That means you have to manipulate this IR register inside a stack instead of registers. So it is basically kicked out to the memory instead of residing in the architecture register. That is much faster. And after spilling an IR register, you have to begin again and draw interference graph again and see if you can successfully color the graph. And if so, we are done. And if it is not, you spill again and again until you get a good coloring. Okay, that is the overall algorithm. And in this lecture, we'd like to discuss a little bit more about each step. How to draw interference graph and how to color the graph and how to pick a spill register and how to place memory allocations and memory manipulations for spilled registers. And also we'd like to discuss a few architectural details that needs to be taken into account when you implement this register allocation algorithm. So let me first explain how to draw interference graph. So recall that in an interference graph, two registers are connected to each other if their live ranges are overlapping. So recall that a register's live range is from definition to its uses. And there can be many uses, so this live ranges is not just an interval. It is basically a union of multiple intervals. And each interval is from definition to a use, and the live range is the union of such all ranges from where a register is defined and to where it is used. And from the SSA property, we know that all definition is dominating all its uses. So it is actually interval. So there is no the use is always later than definition. So we can say it is from definition to uses. Okay, and we have a second property, which is that a use may not dominate to the other uses. So two uses may not dominate each other. So there can be parallelly existing. And as a result, we need to deal with a set of intervals instead of a single interval. So that is the property 2. Okay, this is the register's live range. And now I'd like to discuss how to check whether the live ranges of two registers are overlapping or not. And it is very simple. So let's assume that R1 is the register and R2 is the second register. And R1 is defined in D1 and it is used in U11, U12, blah, blah, and U1n. So there are actually n use cases here. And there is only one definition, D1. And similarly, we have a second register, R2. And then let's assume that it is defined at the definition point D2. And it is used in multiple times in U21, U22, blah, blah, and U2m. So it has only one definition point as dictated by the SSA property, and it has multiple use points, U21 to U2m, because a register may be used in multiple times. And recall that, as I said in the previous bullet point, these uses, U21, U22, U2m, may not dominate each other. They can be just coexist without dominating each other. And here is the condition for checking whether two registers' live ranges are overlapped or not. So So basically, overlapping means that two registers definitions should coexist at some point of time, right? And if you have to remember that the values of these two registers at the same time at any moment, then they cannot be allocated into the same register. And as a result, we are checking whether they are defined at the same time. Their definition is necessary to be remembered at the same time, basically. And you have to check only two things. First, if two registers should remember its values when R1 is defined, they are overlapping. So, furthermore, if two registers should be remembered at the time that R2 is defined, they are also interfering with each other. So this is basically the first condition. D1 dominates D2 and D2 dominates U1I for some I. That means that at the time that D2 is defined, D1 is defined earlier, and that is necessary. That value, the D1, the registers R1's value is necessary after the R2 is defined. So that's the second thing. D2 dominates some use of R1. So to summarize, this line means that this R2 is defined later than R1, and at the time that R2 is defined, R1's value should be remembered. That means these two registers are interfering with each other. On the other hand, conversely, if D2 dominates D1 and D1 dominates some use of R2, then it means that at the time that R1 is defined at D1, the R2 has already been defined, and its value will be used later than R1 is defined. And as a result, at the time that R1 is defined, or at D1, two values for R1 and R2 should be remembered at the same time. So they are interfering with each other. So this is basically the overlap condition. If either of that happens, then these two registers are overlapping with each other. Otherwise, if this is false for all uses, then they are not interfering with each other because their live ranges are not coexisting at any point of time inside the program. So this is the correct and complete condition for checking whether two registers' live ranges are overlapping. Okay, this induces a very naive algorithm. So you first look for two registers and in a nested loop, and you check whether these domination relations are true for each combination of definitions and uses. And it will induce a very inefficient algorithm, but anyway, it will be correct. And for the purpose of this course, let's stick to inefficient and yet correct algorithm. You can also implement efficient algorithm. You can also design and implement an efficient algorithm for checking the live range interference, but you don't need to do that for this course. So if you're interested, you just look for some references and implement on yourself. And one thing to clarify is that in the previous lecture, I mentioned conflict graph instead of interference graph because the registers are conflicting with each other. That is the idea behind it. But other people's, so this concept is usually called an interference graph, and other people, all of them uses the word interference graph for this concept. So I changed the name. It is no longer conflict graph. It is now interference graph. So this is so far is about interference graph, and let's move on to the next key concept, which is coloring the interference graph. So basically, you need to give colors to each vertex inside interference graph. And the question here is, how to give them colors so that we can use as fewer color as possible for coloring the vertices. So every vertex has to be colored, and every adjacent pair of vertices should be colored with different colors. And how to color all of those vertices with as fewer colors as possible. That's basically the problem. And here's the key idea. So here's an observation, basically. If there's a vertex that its neighbors are all fully connected to each other, then it is very strange vertex, right? So a vertex has many neighbors in the interference graph, and they are all connected to each other. Then, as a result, this vertex should have different colors to all of those neighbors, and all of those neighbors are already colored with different colors. So you need to find a new color for this vertex. So we are going to find such a vertex in the algorithm. So that's the reason is that it is only beneficial to color this vertex whose neighbors are fully connected to each other at the end, because after coloring all the other neighbors and all the other vertices, this vertex, the one we picked, can be later colored with the remaining color. Or if there's no remaining color, we should use a new color and use them to color this vertex. So the meaning is that, so here is basically a recursive algorithm. You pick such a vertex whose neighbors are fully connected, and you just remove the vertex from the graph and color the resulting graph that doesn't have the vertex we just picked. And after that, you are trying to additionally color the removed vertex, and this color is very easy to determine because the neighbors are fully connected, so they are colored with different colors, and we need to pick a remaining color that is not used in the neighbors. You just pick one. You can just pick anything from the remaining colors that is not still used in the neighbors. If there's no such color, then you are inevitably needing to use a new color, because all the neighbors have different colors and they used up all the remaining colors. So I have to use a new color, and it is unavoidable. You should do that. So that's the reason why it is an optimal strategy to color the vertices. So if there is a vertex whose neighbors are fully connected, then you just remove it, color, and then additionally color this removed vertex using this strategy. That will give you the best recursive algorithm for coloring a graph. And now, if there's no such a vertex, so it may happen, just the heuristic strategy would be just pick one that will be colored at the end, and color the remaining graph, and then later color the picked one. So this picking procedure is arbitrary. You are not going to pick in a deliberate manner. You just pick one, but that's okay. It will give you anyway coloring, a good coloring basically. The theorem is that for an SSA program, we can always find such a vertex. So this is already proven by some graph theorists, and that means that for SSA program, if you draw interference graph, you can always find a vertex whose neighbors are fully connected to each other. Even after removing a vertex from this interference graph, this property still holds. You can find a vertex whose neighbors are fully connected to each other, etc., etc., etc. So it is basically because SSA has the domination relation and all the users are dominated by definitions, but the deep theoretical results are default to further courses or some papers in the graph theories. Anyway, just memorize that SSA programs always have such a vertex whose neighbors are fully connected to each other. Okay, and as I said, you can color the remaining graph recursively and then color the picked one for vertex. Regardless of whether it satisfies this property or not, you're going to color this vertex in the last step, and you can just choose a remaining color, or you should use a new color depending on the original existing coloring. Okay, this is basically the coloring algorithm you may want to implement as your register allocation algorithm. And if the coloring number is less than or equal to the number of architecture registers, then we are done. And we can just map all those vertices, which represents an IR registers, and we can give a architecture register to all of them. And we have a property that from the coloring constraint, all interfering registers, if a register R1 interferes with register R2, they are mapped to different architecture registers, and therefore they can coexist in the CPU. So, and multiple IO registers may be mapped to the same color, which represents same architecture register, but that's okay because these IO registers may not exist. Should not coexist at the same time. At one time, only one of those IO registers should exist, and that's the reason why we can map all of those into the same architecture register. Okay, so far so good, and let's move on to the next topic, which is finding a register to spill, basically. And suppose that your coloring is not fit to the number of architecture registers. And if that is the case, you cannot map all IO registers into architecture registers. And as a result, you need to somehow give up to map a register, an IO register, to map into an architecture register. So one of the register should be picked, and it should go to the step instead of architecture register. Okay, that is basically the high-level goal of this spill procedure, and there may be multiple possible algorithms for this. So there can be multiple choices. So I'm going to explain each of them, but none of them will be optimal in the sense of performance or optimization efficiency. But let me somehow describe all of them. The first algorithmic choice would be picking a vertex in a clique of size that is bigger than the limit. The limit means the number of architecture registers. Here, the clique means that a set of vertices that each pair of vertices are connected. If all vertices are connected to each other inside a set of vertices, then that is the clique. And clique has a very good property in coloring. So if there is a clique of size 5, and all those 5 vertices should be colored with different colors because they are connected to each other, fully connected to each other. And as a result, this clique is fundamentally increasing the size of the architecture registers that is necessary to allocate registers. And in particular, if there's a clique whose size is bigger than the number of architecture registers, then it is going to be pain. And it is obvious that some of the vertices should be mapped to stack instead of registers. And as a result, pick just one. Pick a vertex inside the clique of size that is bigger than the number of architecture registers. And it is going to be spilled. Okay, there can be other algorithmic choices. For example, in the second algorithmic choices, you can just pick up vertexes that increases the coloring number beyond the limit during the coloring algorithm. So recall that in the previous slide, you're going to use a new color when a vertex is not cannot be colored with the remaining color. If the remaining colors are used up, then you need to create a new color and map this new color to this vertex in the recursive algorithm. And if that happens, and the number of the coloring number just exceed the number of architecture registers, then this vertex is going to be rendering this whole register allocation impossible. So let's make it spilled. So that's basically the algorithmic choice 2 here. Pick a vertex that just increases the calling number beyond the limit during the calling algorithm, which is recursive over the graphs. And after spilling this vertex, the recursive algorithm will likely proceed more. It is not guaranteed that after splitting this vertex, the allocation is successful, but it will proceed further steps. The third choice here is picking a vertex whose life ranges span many instructions, basically. So it is similar to choices 1 and 2 in that it is picking a vertex whose life range is long, which means that it is likely to interfere other IO registers much. But it is not a very precise measure. I mean, it is basically a property of the program, but in the register allocation, we may need to want to take into account the property of registers. So, but you can see that all these three algorithmic choices have the same spirit. If a vertex is a pain in the coloring, then just make it spill and allocate them into stacks. As I said, there is no clear winner in these greedy algorithms, and there is no optimality theorem about the spill algorithms. But in my experience, choosing any algorithmic choices would be working. Would be efficiently working. So you can just pick one of those algorithms and see what's going on there without sacrificing a lot of performances. Okay, and after picking a register to spill, then you need to allocate the location inside the stack for those spilled registers, and you need to convert all register read-write into a memory load store. So if an IO register is read, and you first need to load from the stack, spilled stack basically, and then use it. Furthermore, if you write a value to the register, you need to, in addition, you need to store this register, this value that would have been written in the IO register into the stack location. So basically, register read-write should be transformed into memory load store for these spilled IO registers because these registers are mapped to the memory locations in the stack. Okay, let me finally explain the architectural constraints that affects the register allocation algorithm here. And RISC-V, as well as all the other architectures, have some constraints that affect the register allocation. So here are the examples here. For example, arguments should be in A0, A1, and blah, blah, and to A7, which are argument registers. So they should be in the argument register when a function calls the other function, when argument is passed from the caller to callee. And furthermore, these argument registers should be residing in this A0 to A7 at the beginning of the function. So at the beginning of the function, if the function foo has two arguments A and B, A should be mapped to A0 and B should be mapped to A1 register. And how to guarantee such property? How to guarantee that A and B should be mapped to A0 and A1? Because the coloring algorithm doesn't care much about the assignment. And here you are going to convert this function foo A prime B prime into A equals A prime and B equals B prime. And then A and B will no longer be arguments. They are just normal registers that can have any colors. But here, A prime and B prime becomes the argument registers. They are and then fixed to A0 and A1 in the allocation. So the idea is simple. You first transform the program into this form in such a way that argument registers are used only once. They are only copied from, and they are fixed in the coloring. So at the beginning of the coloring algorithm, you just fix the coloring of A and B into A0 and A1. And you are going to color other registers, including A and B, according to the previous mentioned coloring algorithm. And in that way, you can just use all the, you can just plug in this architectural constraints into the coloring algorithm. Okay, so far so good. And you should do similar things for function calls as well. If you call this function foo, then you need to place the arguments inside A0, A1, A2, blah blah, and you similarly do a copying, so that these registers in our argument registers are only defined just before a function call. So that is basically the idea for translating a function entry block and function calls, so that these architectural constraints are taken into account in the register allocation. Okay, so far so good. And let's move on to the second constraint, which is color save registers. They are not preserved after function calls, right? If T0 is 42 and you call a function foo, then the function call foo may change the content of T0. So after this function call, T0 may contain, for example, 37 or 66, blah blah blah. So we need to somehow express that idea inside the coloring algorithm, right? And we need to regard this call function foo changes a virtual IO registers that is correlated to the T0. So we do this like this. So we introduce virtual registers for T0 inside for this function called foo. And as you did for the argument registers, you hardwire this virtual register into T0 in the coloring at the beginning of the coloring algorithm. And furthermore, you are going to color all these registers, and because of these virtual registers that is just defined in T0, all the IO registers before this call function should be colored differently. They should be colored different than T0 basically. So in that way, we can express the idea that this function call may change the contents of T0 to T11, the temporal registers, thanks to these virtual registers that are hard mapped to T0 to T11. Okay, that is basically the idea. And for argument register allocation, I need one more thing to discuss. If I said that we introduce a register copies at the beginning of a function and a function call. A becomes A prime, B becomes B prime, etc., etc. And if these two registers are mapped to the same color, then we can completely ignore this assignment and just doesn't translate anything from this assignment. So a prime is hardwired to a0 because it's an argument. And if a is mapped to a0 as well, then we are effectively copying a0 to a0, which should be no-op. We don't translate this instruction into any meaningful architecture instructions. And such an optimization is usually called coalescing. We are coalescing multiple registers into a single architecture register so that we can reduce the number of copies. So we can apply such optimizations if A and B are mapped to A0 or A1 respectively. And let's move on to the next constraints, which are the two. And the first thing is that an ARIA register may be too big to be fit in an architecture register. So for example, KCC allows a register to be a struct type, and it may have, for example, 100 bytes of data. And it is obviously not fit into an architecture register. How to do that? A simple answer would be that let's allocate it inside stack always. So struct registers are never allocated inside architecture register. They are always in stack. And if you need a value, you just load a part of it and calculate things, and then you store a part of that inside the structure stack. That is a simple answer. I recommend you to do that because it is a simpler answer. But there can be a more complex answer, which is basically dividing on a big struct into multiple smaller registers. So if you have an array of 100 integers, then you can just split them into 100 integer registers. So after doing so, after splitting them into multiple smaller registers, you can fit all of those into architecture registers. But I don't recommend you to do that in the final project because it will take more time for you. If you can, I strongly encourage you to do, but it is not strongly recommended for the purpose of final projects. So this kind of optimization is usually called SROA. I forgot the long name of this SROA. Oh. It is SROA is the scalar replacement of agreements. So structs are aggregates, and they can be scalarly replaced. So that is usually called scalar replacement of aggregates, or SROA. Okay, so far so good. And the final constraint we need to consider is that integer and floating point numbers have to reside in different set of registers. For example, T0 to T11 is integer temporary registers. On the other hand, FT0 to FT11 are floating point number temporary registers, and they are different things. You need to allocate integer registers into integer registers and floating point number registers into floating point number registers. And in order to do that, you need to allocate each data type registers separately and do that. You need to allocate IR integer registers into architecture integer registers, and similarly for floating point numbers as well. So in the coloring algorithm, you just can use two sets of colors instead of one set of colors. So by doing so, you can safely allocate the registers into the corresponding set of registers. Okay, these two slides explain some architectural details that needs to be taken into account when you implement register allocation. And if you need to study more about register allocation, here are a few references. The first set of references are explaining register allocation algorithm for SSA. And here is a great slide due to Sebastian Heck, who is a professor in the Saarland University in Saarbrücken, Germany. And he's the inventor of the register allocation algorithm for SSA. And this slide and this PhD thesis contains a lot of useful and enlightening information on the SSA's register allocation algorithm. And furthermore, there are formal verification work of register allocation, which basically explain why register allocation optimizations are correct with respect to the program language semantics of these IRs or IRs in assemblies. And Ridio and Leroy published a paper on and formally validating register allocation and splitting. And Blazy and the collaborators published a paper on formal verification of optimizing register allocation in a similar venue. So if you are interested in how to know whether it's correct, how to know whether register allocation is correct or not, I recommend you to read these papers. So this is basically the end of the register allocation slides, and it briefly touches the implementation details of these algorithms. And so I hope you can start implementing your own register allocation algorithm in your project. So if you are not sure about any details, please ask questions in the issue tracker, or you can consult the slides and PhD thesis of the Sebastian Heck, and it will be a great source for you to start working on register allocation.